Alright, today we're going to continue our investigation into solving systems of equations. We're going to look at solving systems of 3 equations and 3 variables. We'll also introduce using matrices to help us solve systems of equations. Now, we can still use the techniques that we've discussed previously, so we could still use substitution or graphing, but graphing specifically gets a little bit more complicated with 3 variables because then you have 3 dimensions, and so that's not something that we can easily do on our calculator or on a pencil or paper. Substitution also still works, but since we have more variables, then it becomes more complicated to be able to isolate a single variable. So elimination is going to be our best technique to use. Our goal when we're using elimination for a system of equations with 3 or more variables will be to eliminate one variable from a pair of equations, and then we'll try to eliminate the same variable from a different pair of equations. This should leave us with 2 equations that involve only 2 variables, so it goes back to the same type of problem that we've been working on before. Once we've solved for those 2 variables, then we can work backwards and solve for the final missing variable. So let's take a look at this example that we have here. The first thing that we'd like to do is eliminate one variable. It doesn't matter which variable you choose, there is no correct answer as to which variable to choose, but a good general thing to keep in mind is you'd like to try to isolate a variable that's easy to manipulate. So I'm going to try to isolate the x because the x already has a coefficient of 1. So that means it's going to be easy for me to multiply the first equation by any constant to make it match and eliminate with another equation. For ease of notation, we will call the first equation E1. Oh, here we go. We'll call the first equation E1 for equation 1. The second one will be E2, and the third will be E sub 3. You want to get used to denoting things with indices like this. So a subscript lower than the letter to indicate which number it is, because we'll use the same notation when we get to matrices later on in this section. So let's go ahead and pair off the first 2 equations. So equation 1 and equation 2. And my goal is going to be to try to eliminate the x. And again, I've chosen x because it has a coefficient of 1. I could have just as easily chose the y in equation 1 or z from equation 2 or equation 3. So this is just one of many ways we can do this problem. So if I'm pairing off equation 1 and equation 2, and I'd like to eliminate the x, that means that in equation 1, I really need negative 2 x's, so that when it combines with equation 2 by addition, we'll be left with no x's. So I'm going to take negative 2 times equation 1, and I'm going to add it to equation 2. Sorry, not equation 3. Equation 2. Creating a new equation that should have only 2 variables. So let's go ahead and show the arithmetic for that. Negative 2 equation 1 means we have negative 2x minus 2y minus 4z equals negative 24. And plus equation 2 means we have plus 2x plus 3y minus z equals negative 2. So we combine like terms, so negative 2x plus 2x gives us no x's, negative 2y plus 3y leaves us with 1y, and negative 4z minus z leaves us with minus 5z. Negative 24 minus 2 leaves us with a negative 26. So we now have a new equation. It only involves 2 variables, and if we can come up with a second equation similarly with only 2 variables, specifically y and z, then we'll be able to solve for those 2 variables. So now, let's go ahead and look at combining equation 1 and equation 3. Again, I'm sticking with equation 1 because it has a 1 coefficient for the x, so it'll be easier to work with. So if I want to eliminate the x by combining equation 1 and equation 3, that means I'm going to need 3 copies of x in equation 1. So we will take 3 equation 1 plus an equation 3, and this new equation should eliminate the x. So let's see, 3 times equation 1 that would be 3x plus 3y plus 6z equals 36, plus E3, which is negative 3x plus 4y plus z, and this is negative 8. So combining like terms, 3x and negative 3x combine to 0, x's, so we've eliminated the x term. We are left with 7y plus 7z equals 28. So now we have a new system of equations that we're trying to solve, and that system involves only the variables y and z. So that system we would like to solve is 7y plus 7z equals 28, and y minus 5z equals negative 26. So now that we have a system of two variables, we can go ahead and use any of the techniques that we've discussed before. So in this case, I'd like to use substitution, since we have one coefficient on the y in the second equation here. So let's see, we have that y is equal to 5z minus 26. Okay. And now we can go ahead and substitute that in to the first equation from our secondary system here. So we get 7 times 5z minus 26 plus 7z equals 28. When we distribute the 7, this gives us 35z minus 182 plus 7z, my 2's and my z's are very confusing, equals positive 28. Combining like terms and moving the constant to the other side, we end up with 42z equals 210. And so finally we can solve for z, and z equals 5. Now that we have a solution for z, we can easily get a solution for y. Y has to equal 5 times 5 minus 26, which would be negative 1, because 5 times 5 is 25. And now that we know z and y, we can solve for our final variable, x. Now to solve for x, you can use any equation from the original 3. It doesn't matter which one you use, so I'm just going to use the first one, but it doesn't matter which one we're going to use. So using the first equation, we have, let's see, our equation is x plus y plus 2z equals 12. So we have x plus negative 1 plus 2 times 5 equals 12. So we have x plus 9 equals 12, and so x is equal to 3. So our final solution then is the xyz point 3, negative 1, 5 as a coordinate pair. Okay. So the main thing that I want you to keep in mind when you're solving systems of 3 or more equations using elimination, you have to work in pairs eliminating the same variable. So this would not have worked if we had eliminated x from the first pair, but then say maybe we eliminated y from the second pair. Then we wouldn't end up with a system of 2 equations with 2 variables. So it's important that you always eliminate the same variable from both pairs of equations. Alright, that's it for now.